The purpose of this video is to review basic concepts of stress analysis of beams under bending. Let us begin with introducing coordinates. We choose the origin of the coordinate system at the centroid of the left section. In our case, we pick a T section for demonstration, but any section is fine. The x-axis goes along the bar. The y-axis is vertical and it points down, and the z-axis is chosen so that the x, y, z coordinates form a right-handed coordinate system. We'll be using both the side view in the xy plane and the cross-sectional view in the yz plane. We will rely on the standard convention for the internal forces. So the bending moment and the shear forces are shown on this infinitesimal element of length delta x, and the entire picture is in the xy plane. Let us begin with the normal stress. For the given formula, the moment m of x is obtained by constructing the bending moment diagram. The other two quantities, y and iz, are obtained by looking at the cross-section. So the y coordinate refers to the point of interest, and iz is the moment of inertia with respect to the z-axis. For the shear stress, the formula is a bit more complicated, but there are similar features as in the previous formula. In particular, we start with identifying the shear force diagram for V. Iz, Q of y, and B of y are cross-sectional entities. To define them first, we identify a point of interest shown here by a big dot. Then if we look at the horizontal line going through this point, we identify the width of the cross-section, B of y, and we identify the area A star below this cut. And this is shown as a green area. So Q, by definition, is the first moment of A star with respect to the z-axis. Iz, as in the previous slide, is the moment of inertia with respect to the z-axis. Let us consider rectangular cross-sections. So the cross-section base is denoted by B and height by H. Then we can immediately identify the moment of inertia, Iz, and two interesting values of y. The maximum value of y is at the bottom, equal to h over 2, and the minimum value is minus h over 2, and it is at the top. Now we can calculate the stress by substituting the moment of inertia into the basic equation to obtain this expression, and we can further evaluate it at the extreme values of y to obtain the values of max and min stress using this formula. The presence of pluses and minuses deserves some attention, and that's what we're. Let us rewrite the expression on the previous page and evaluate it for positive bending, where the lower part of the beam, or positive y, is in tension, shown in red, while the upper part for negative y is in compression. Here you could see minus, which indicates that the stress is compression. Alternatively, we could have written that this is compression of the magnitude 6m over bh squared. Now, if we look at the case of negative bending, then we see that there is a flip. Now, the bottom is in compression and the top is in tension. The values do not change. And the bottom line of this is that one has to be careful and nothing else, really. Now, for the shear stress, the formula is written in this way, and we know IZ. And to calculate the remaining quantity Q of y and B of y, let us identify the point of interest somewhere along this line, and the y coordinate is shown here, and below this line shown in green is A star, and let us also have a separate picture for A star that will help us to calculate Q. Indeed, Q, the first moment of the area, could be calculated as the product of the coordinate of the centroid of A star times the area itself. And here's the calculation, which here exploits the fact that the centroid of the green area could be computed as the average between the coordinates of the upper fiber with the coordinates y and the lower fiber with the coordinates h over 2. There are other ways of arriving at this expression, but all of them really lead to the same result. So once we simplify things a bit, we obtain the expression for the shear stress. One can easily see that this expression maximizes tau when y is equal to 0, and therefore we obtain the expression for the maximum tau. Please pay attention that V over BH is the average stress, so of course the maximum is larger than the average. Let us revisit this result a little bit. So we rewrite the equation obtained on the previous page, show A star, and we want to choose the case of positive V. In this case, tau as a function of y at a fixed x is a parabolic distribution. So the maximum shear stress at y equal to 0, or along the x-axis, or on the neutral line, and the direction of the shear stresses are fully dictated by the direction of the shear force on the corresponding cross section.